Howdy, I'm the amateur logician, and to me at least, it's fascinating how the human mind confronts a difficult mathematical problem. We often have no idea what the solution is immediately, but sometimes we can manipulate or transform the problem, so to speak, into a pattern or form that is recognizable to us, and where that specific pattern or that specific form we do know how to solve. For example, think about completing the square in high school algebra. Essentially, we're transforming the equation in such a way that we can now easily solve it. And in our analytical approach to differential equations, we can do something analogous to completing the square. That is, we can sometimes find so-called integrating factors. So let's say we have the first order linear differential equation dy dx plus p of x times y is equal to q of x. We want to solve that. We're going to do that through a so-called integrating factor. So first off, we're going to multiply that entire equation by v of x. So now we have v of x times dy dx plus v of x times p of x times y is equal to v of x times q of x. We have a goal. What we want to do is to transform that left-hand side into the derivative of the product v of x times y. In other words, we want d dx of v of x times y. And the right-hand side is just v of x times q of x. Because if we can do that, we can then anti-differentiate both sides. We have d dx of v of x y. We can anti-differentiate that. And we can anti-differentiate the right-hand side, v of x, q of x. It's also with respect to x. Because on the left-hand side, we know about the fundamental theorem of calculus, integration, and differentiation, so to speak, are inverses of each other. So the left-hand side is just v of x times y. The right-hand side remains the same. But now we can solve that y is therefore equal to 1 over v of x times the indefinite integral of v of x times q of x dx. And that's a great solution. We have solved our differential equation. But the question is, what is that v of x? Now remember, we've stipulated that this expression here is equal to this expression here. So this should allow us, hopefully, to solve for v of x. So let me write this out to be more explicit. We want d dx of v of x y to equal this expression here. So v of x dy dx plus v of x p of x y. All right. So those are equal. But to solve this, we'll have to apply the product rule to this left-hand side. And remember that the product rule is the following. So let's say we have uv prime. That's just equal to uv prime plus vu prime. So if we apply that to this, we thereby get v of x dy dx plus y dv dx. And the right-hand side is just this expression. So we have v of x dy dx plus v of x p of x y. So the question is, what is v of x equal to? Because that's our integrating factor. That's what allows us to transform the equation into something like this so that we can easily solve for y. All right. Well, look that this expression appears on both sides of the equation, so we could subtract that from both sides of the equation. The equation still balances, so to speak. So now we have y dv dx is equal to v of x p of x y. Here's a y, here's a y. We can divide both sides of the equation by y to further simplify it. So now we have dv dx is equal to v of x p of x. We still want to know what v is. But look, right here, we actually have a separable differential equation. And we know how to solve that. And so we can say we have dv over v of x is equal to px dx, and we'll enter differentiate both sides. What's the left-hand side? And we're not going to worry about absolute values here. That's just equal to the natural logarithm of v of x. We can't do anything to that right-hand side. That's just the indefinite integral p of x dx. We want to solve for v, so we'll say we have e raised to the following power. E to the following power. These, of course, are inverses. So now we have v of x is equal to e raised to the indefinite integral p of x dx. And so now we have solved our integrating factor, which is also often called mu. So we have mu is equal to e raised to the indefinite integral p of x dx. So this is our integrating factor. And we can solve any good first-order linear differential equation with an integrating factor, because what we're doing is we're forcing it into a pattern, a structure that we can easily solve. Because we're going to end up in a situation like this. And then we can get exactly what y is equal to. Pretty cool.